Okay, well, welcome to the last session. My name is John Francis. I'm a senior research scientist at Bosch and also CBI mentor and area chair for robotics. We'll have the last session including some of our postdocs. So I'm happy to start to introduce Evan. So Evan Spotte Smith is a computational and data chemist with a background in materials science, electrochemistry, and energy storage. The research focuses on leveraging computational simulations and data science to understand reactivity in complex systems, including electrochemical interfaces and solid-state syntheses. Evan obtained their PhD in materials science and engineering from Berkeley. They are currently a CBI postdoc fellow at CMU here, collaborating with Professor Rachel Kirchen in materials science and engineering, and previously completed a postdoc with Professor Gabe Gomes in chemical engineering and chemistry, also here at CMU. Evan is an incoming assistant professor of chemical engineering, and their focus of the talk today is on rational design of sustainable technologies with data-enabled reactive simulations. So Evan, please take it away. Thank you.
Yeah, thank you so much. Well, this title's not very appropriate anymore, and we'll get to why in a minute. But I always like to start these talks with acknowledgements. Of course, I'm extremely grateful to CBI for giving me a lot of freedom in terms of research direction and allowing me to explore some new directions in my work. As you heard, I'm an incoming assistant professor, and so I also have some startup funding from CMU that I'm extremely grateful for, especially as the funding situation in the US is quite hostile right now. And I have a grant from Toyota, although that is nowhere near related to the work that I'll be presenting today. Computing resources come from NSF Access as well as the National AI Research Resource. So a little apology. So I originally wanted to talk about sustainability and using artificial intelligence, machine learning to better understand sustainable technologies. But I was really, inspired by the title of this symposium. I, as a chemist, I know a lot about sustainability. I think a lot about sustainability. But what does it mean for a chemist or any domain scientist to be using artificial intelligence responsibly? This is something that I think my field has been extremely uncritical of. We're adopting these technologies like large language models, and there's not really a lot of discussion in the literature about how they're used, if we should be using them, where we should be using them, etc. Now, I am not a philosopher by training, even less so than I am a computer scientist or a data scientist by training. But if no one else was going to do this work, someone had to. So I recently wrote this piece considering the ethics of large machine learning models in the chemical sciences. It's in review now, preprints on ChemArchive. And the basic idea was to open a conversation. So to think critically about what are the ethics of chemistry, what is good and moral right in chemistry, what is the goal of chemistry and related fields, to what extent are large models, basically foundation models, and I'll define that in a little bit more detail, like the context that I'm speaking of, how are these models compatible or incompatible with established chemical ethics and scientific ethics? And if they're incompatible, I need to stop pressing that button, what can be done to sort of resolve these ethical incompatibilities and these challenges? All right, so crash course on scientific ethics and chemical ethics. So there's a lot of different sort of ideals that have been laid out in the literature since the 1940s of sort of what are the principles that guide scientific research. I decided to focus on one that was recently published by the National Academies of Sciences, Medicine, and Engineering. The reason I chose this is with such broad representation, I figured that it should be inoffensive to many people, and most people should generally agree on these principles. And these ideals include objectivity. This is kind of problematic. Humans can never be objective, but scientists, we try very hard to be objective. Honesty, openness, accountability, which means basically that you need to be able to stand behind what you've said and what you've done to your peers in the scientific community as well as to the broader community. Fairness as well as stewardship. And stewardship refers to creating and maintaining relationships, again, within science as well as between science and the broader world. Okay, now in addition to scientific ideals, I thought about professional ethics because as a practicing scientist, I never signed on to those ideals. Those are sort of some thinker somewhere came up with them and wrote them down. But I did agree to follow professional ethics. So I'm, for instance, a member of the American Chemical Society. To be a member, I had to agree to ACS's Code of Ethics. So hopefully all chemists agree to what they signed on to. And I actually sort of synthesized a couple of different professional ethical codes, including from the ACS and the American Institute of Chemical Engineers, as well as some less US-centric codes of ethics, the Global Chemist Code of Ethics, as well as the Hague Ethical Guidelines from the Organization for the Prohibition of Chemical Weapons. And compiling all of those resources, I came up with a small set of sort of general ethical rules that chemists and chemical practitioners need to follow. We need to work to ensure current and future well-being. The future part is really important here because we're operating under very extreme uncertainty a lot of the time. We don't know how our technologies are going to be used or what the impacts of our research is going to be, and especially for folks like me who do a lot of basic science work, that's particularly severe uncertainty. We need to share openly and with attribution. The with attribution part, very important. If we're sharing someone else's ideas, we need to give them proper credit. Avoiding what I consider to be sort of intrinsically bad activities, plagiarism, harassment, discrimination, these sorts of things. Increasing knowledge by speaking truthfully and openly. And you'll notice here, there's a lot of overlap between these professional ethical guidelines and these ideals. And finally, protecting public health, safety, and security. Okay, so we have our ideals that we would like to follow. We have our professional ethics that we are required to follow. Now, how do these align with foundation models, like, for instance, large language models, image generators, or vision language models? For this talk, I'll mostly be speaking from the perspective of LLMs, because that's mostly the general purpose foundation model that's been applied in chemistry. Or the family of foundation models. But I'll also speak about what I consider to be chemistry-specific foundation models. So for instance, there's been a lot of focus recently on protein models. These are models where you take as input a string of amino acids, and the output is a 3D protein structure. This is sort of credited with solving the long-standing problem of structure prediction in structural biology. And for that reason, the 2024 Nobel Prize in Chemistry was awarded to researchers who developed these protein models, these foundation models for structural biology. Another example would be so-called universal machine learning interatomic potentials. So an MLIP, this is a model that takes as input a molecular or material structure, your XYZ coordinates of all your different atoms and what their identities are. Is it a carbon? Is it a hydrogen? Is it an iron? What have you. And the output of the model is an overall system energy and an atom-wise force, with which you can do a lot of different things. The most common use is molecular dynamics. So you're just propagating Newton's laws of motion forward in time. You're seeing how your system evolves chemically over time. And now the reason we call these universal models is we have data sets that are sufficiently large and models that are sufficiently complex that they can span basically the entire periodic table. Still not perfect, but certainly I would consider this to be in this category of foundation model. Okay, now thinking about general purpose foundation models, so again, your LLMs, your VLMs, your diffusion models for image generation, we have a couple of different major risk categories. And I won't belabor these because a lot of the previous speakers in this symposium have already touched on most of these ideas. Large language models and other foundation models reproduce hegemonic biases. They're racist, they're sexist, they're ableist, they're transphobic and homophobic, etc. They violate privacy. They often leak private information. This may seem to be irrelevant to chemistry, but oftentimes we're using medical information. Medicinal chemistry, biochemistry are very significant areas of research interest in chemistry. And then there's epistemological risk, and I don't think this has been touched on in this symposium. There are sort of two major branches of epistemological risk. First, a speaker yesterday said that large language models lie. That's actually not very precise. To lie means you know what the truth is and you choose to say otherwise. Large language models have no understanding of truth whatsoever. They are trained to predict the next token, the statistically likely next token, and because humans are very good at saying things that are wrong and very good at lying, the next word that appears in a sentence can never be guaranteed to be true. So in precise philosophical terms, LLMs are not liars, they are bullshitters. And that actually is a real philosophical term. Look up Frankfurt 2008 on bullshit. The other epistemological risk that arises from these foundation models is they sort of take away our ability to reason. They do that in a couple of different ways. They could create something that looks very realistic but is false, so like a deep fake, which we heard about earlier today, in terms of audio or video or images or what have you. But also there was a recent paper from Microsoft that showed that people who rely heavily on large language models actually use critical thinking less. And they change how they engage in critical thinking. So, this is early days and this research is still immature, but it seems plausible that our actual way of reasoning and understanding things in the world could fundamentally change because of these technologies. And for science, which is a truth-seeking enterprise, that's extremely dangerous. Plagiarism, don't need to go over that. Labor, a previous speaker went into the changes in the labor market that could occur because of AI in great detail. One thing that I will add to that discussion, which was not touched on very much, is whatever the courts say about foundation models, training these models, especially the commercial ones, typically requires theft of intellectual property and creative labor on a scale that's never before been seen in human history. And actually, one other thing that I'll add, it's often assumed that the impacts of foundation models, large language models, AI, what have you, is primarily going to go to unskilled or low-skilled workers. And there's actually preliminary data that shows that that's not the case. There was a study that came out, I think last year, it might have been late 2023, that looked at freelance workers and saw that actually the freelance workers that had the highest output and the highest quality as measured by satisfaction reports of customers, whatever, had the greatest impact in terms of their sales and income as a result of the deployment of generative AI. Okay, finally, environmental and climate degradation. This has also been talked about to death. Okay, so we have these sort of 6 horse people of the apocalypse. How do they line up with our ideals? This is, of course, very subjective, as pretty much all philosophy work is. But I tried to break these down. How do these various risks threaten or impact our various scientific ideals? And I won't go through this point by point, but what you should see from this slide is basically all of them are threatened except for openness. And openness, as long as you're transparent about how you're using these models, that's fine. But everything else is threatened. Because these models are prejudiced, they're not objective. Because they're prejudiced, they can't be fair. Because they damage the environment, that threatens stewardship, damaging our relationships with broader communities and non-human populations, and so on and so forth. But as I said a few slides ago, who cares, right? These ideals are not necessarily things that we have to follow. So what about the actual ethical requirements of our professional societies and our chemistry community? It's even worse. All of the major categories of obligations that I identified are negatively impacted by the ethical risks produced by foundation models. Again, I'm not going to go through this point by point. If people have questions, I'm happy to talk about it in some more detail. But my sort of overall thesis is that generative foundation models, as they currently exist, as they're currently trained, developed, deployed, are morally incompatible with the ethical practice of chemistry. Now, I want to emphasize here, I am talking about foundation models and more specifically about generative foundation models, small scale AI or ML models to predict a material property. That doesn't fall under the same category and certainly doesn't involve the same ethical risks. There's also some specific risks that is not part of that big scary figure, the 6 horse people of the apocalypse, that are sort of unique to chemistry, even though they involve general purpose foundation models. So for instance, one area of very active research interest is laboratory automation. And a couple of speakers have actually touched on this. Can we use large language models or other foundation models to, for instance, perform a chemical synthesis? The answer is yes, but in doing so, we introduce 2 major risks. First, there's dual use risk. So actually a group here at CMU, Gabe Gomez's group, my former postdoc advisor, found that they were able to trick an LLM, which was supposedly trained to be harmless, to synthesize compounds that are both deadly to humans. They tricked it into synthesizing chlorine gas. It's a chemical warfare agent. And they were also able to trick these models into producing illegal compounds. I believe the example was THC, which is, of course, a Schedule I drug, although it is legal for medicinal use in the state of Pennsylvania. Another chemistry-specific risk is laboratory safety. So humans, to go in a lab and use a piece of equipment, we have to be trained. So another human has to verify that we are competent in the skills necessary to perform a particular operation safely. And there's also a foundation of trust between humans because of human relationships. I know that you are not going to burn down the lab because you want to remain employed here, because you want to do your own research and you want my research to succeed. The social relationships allow us to have some kind of imperfect but reasonable expectation of safety. An LLM might be able to answer all the questions correctly in a safety test, but you can't have that same foundation of trust. This is not a human person that can be guaranteed in any way to operate safely. And then, of course, you could say, well, the human could oversee the LLM's behavior in the laboratory and thereby guarantee safety, to which I would say, absolutely, but then why are you using an LLM, right? Now, another area of sort of unique risks that arises is, as I already alluded to a little bit earlier in the talk, when we're applying foundation models, generative models, to the study of medicinal chemistry or biochemistry. There have been a couple of studies, I'm citing just one here, that have shown that in addition to being generally racist, foundation models specifically like to advocate for debunked race-based medicine. That's really dangerous. So if we're designing a drug and a subpopulation of interest is, for instance, Black people, one negative and biased outcome of these models is that they believe, or some of them believe at least, that Black people experience less pain than their white counterparts. So if we're designing a painkiller, that's going to lead to disparate health outcomes. And that's just one sort of off-the-cuff example. This is a general problem. The bias of these models becomes a problem in chemistry whenever chemistry is interacting with humans. Okay, now what about these truly chemistry unique and sort of more single-purpose foundation models that are still very large and very complex, but are not sort of trained on the entire internet and are not generating natural text or images? So if we look at this wheel of risks again, it's pretty easy to convince yourself that most of them don't really apply, or at least don't obviously apply. For instance, these models are not going to be prejudiced in the same way that a large language model is because they're trained on amino acid sequences, which say nothing about things like race and gender, or they're trained on material structures. There's going to be human bias involved in these data sets. There's always going to be human bias involved, but it's not going to be the same hegemonic prejudice. Labor is not really an issue because the data sets are typically entirely open source. So protein models are trained on the protein data bank, and all PDB structures by requirement are in the Creative Commons. They have like something like a CC0 or CC BY license connected to them. Really, the only major risk that still applies to these models is the environmental risk. Now, as the last speaker said, there's not sufficient research into energy use, water use, so I can't say exactly how bad protein models or foundation models in chemistry are for the environment. Maybe that's an area for necessary future research, but certainly they are large, on the order of hundreds of millions, maybe billions of parameters. They are complex. They are expensive, especially models that have significant constraints like rotational and translational equivariance. Okay, so given all of that, given that analysis, quo imus, which is Latin for where are we going? Or I might paraphrase and say, what the hell are we doing here? I, as a domain scientist, when I was doing this analysis, I thought about other times in history, modern and further in the past, where chemists have known that they were doing the wrong thing. I've thought about how we've responded in those cases. So one example that's near and dear to my heart, I did my PhD research on batteries. And you might know that lithium-ion batteries, the ones we use in our phones, in our computers, et cetera, they use cobalt for the cathode material. And cobalt is really nasty work. The only place on Earth where it is abundant and where there are ores that are worth mining in terms of the economic profitability is the Democratic Republic of Congo. The problem with that is there are significant labor abuses in the Congo. There's unpaid labor, basically slave labor. There's child labor. And while we are still selling lithium-ion batteries, the community has shifted away from cobalt, especially on the research side, but even in some commercial battery producers. there's been a massive surge towards cobalt-free batteries. So we know this is bad, even though it's truly still the best material we have for lithium-ion batteries, we're not going to use it. We're going to shift away from it. Another example, plastic waste. This has a lot of negative impacts. So what I'm highlighting here is environmental degradation, but it's also terrible for human and animal health. And again, right, we haven't completely gotten rid of plastics. There's still a huge amount of plastic waste being produced, even in our laboratories. But we recognize this is a problem, and we are trying to shift away in two major ways. First, identifying better ways to recycle waste plastics, so decrease the harm that is done by waste plastics, and also developing new plastics that are biodegradable so that they do not contribute to this ethical harm in terms of environmental degradation. So translating that from these historical and modern chemical examples back to foundation models, what should we be doing? And I'm speaking about domain scientists, but maybe this applies elsewhere. Well, just like with the cobalt example, if there's any cases where we can just avoid using these models entirely, we should. We should eliminate all non-essential uses, and I'm listing a couple here. Humans can way more energy efficiently write than an LLM. Human brain's extremely energy efficient. Information search and summarization, code generation, these are not essential for chemists. We can do all of these pretty well as humans, so we should not be using foundation models for them. For applications where these technologies truly are essential, so for instance, we have nothing better than a foundation model for protein folding right now, and there's nothing obvious that can replace those models, we should identify ways to minimize harm. How can we make these models more energy efficient? How can we get the same outcome with fewer inference calls? These sorts of questions should be asked. And then where possible, we should also be pursuing alternative technologies with less ethical risk. So for instance, if we're really trying to automate our laboratories, right now, LLMs might seem like the best tool, but we should be researching alternatives that don't require us to use LLMs, that don't require us to use as much energy, that don't have the same intrinsic biases, etc. So with that, I am basically done with this. I am also very happy to talk about catalysis and sustainability, but yeah, this is sort of consumed my mind for the last couple months, and I'm very glad to have been able to share it in this sort of friendly audience. Thank you so much.
Any questions for Evan?
So I guess I'm curious what your take would be on kind of, and I understand like the ethical risks still exist, but kind of like one more middle ground, which is wrapping LLMs in kind of more traditional technologies to ensure some of the safety. That came to mind when you were discussing like the automated lab use case. It made me think of some of what we do with autonomous vehicles, which is, okay, you've got this large model kind of hallucinating how it's going to be moving through the world, but you still have traditional safety mechanisms within that car to make sure we don't run into a wall, and to like rate limit safety or speed in order to make sure that you can stop in time, questions like that. So I'm curious how you think about that as a potential to, still to minimize the ethical risk, or if it's minimizing maybe the actual risk and not the ethical risk.
Yeah, I mean, that's an excellent point, an excellent question, and one that I actually really didn't go into any depth in working on this paper. I guess earlier today I asked a question of content-based versus context-based risk in chemistry. And I think that same problem arises here, right? So, for instance, the way that they were able to, Daniil Boyko and Gabe Gomez's group, they were able to trick the LLM into producing chlorine gas. If I remember correctly, I might be shaky on this, but if I remember correctly, that was not the main product. So the LLM was, in principle, producing something that was non-toxic, non-harmful, but it didn't realize that in doing so, it was producing chlorine. And it was producing the chlorine gas in a way that was like laboratory safe. It was following, as far as they've told me at least, I wasn't there for this, but it was following appropriate protocols, and it was mixing chemicals safely and all of that. It wasn't just chucking glassware around, but in context, the steps that it was doing was extremely unsafe and potentially harmful for human health. And maybe I lack creativity here, but I really struggle to see any guardrail that allows meaningful chemical research and doesn't allow any like unsafe outcome. Because chemistry is just a really unsafe science if you're not careful, I mean, talk to any fluorine chemist. Like, stuff blows up all the time, even when they're being careful. Yeah. So, does that answer your question? Yeah, I'm sure that there are some like possible harms that you could totally bypass. So, for instance, like if you're doing a high pressure reaction, you could have some kind of maximum pressure cap, and even if the model tries to go off the rails and blow it up, it's not going to be able to, like, things like that. Yeah, I think that guardrails could help you. I don't think it's a full solution.
Any other questions?
Hi. How was the data generated for the like universal foundation models, and like what's the kind of format required for that?
Yeah. So this is, as the previous speaker pointed out, most of the time when we're talking about the environmental harm of foundation models, we don't talk about the data. For those universal MLIPs, people generate massive data sets, massive for chemistry, about 100 million data points of computed energies and forces using typically quantum chemistry software and methods like density functional theory. So if you're not familiar, it's a cheap way to approximately solve the Schrodinger equation for an electron system. It's quite expensive. Generating 100 million data points is I don't even want to calculate what the greenhouse gas emissions are. This is something. So in this paper, I tried very hard to avoid consequentialist ethics, which is basically ethics based on is the end result good or bad, rather than is the thing you're doing good or bad. Because one could argue that yes, you're generating these data points using really expensive calculations, you're generating a bunch of greenhouse gases, but then no one else ever has to generate those same calculations ever again. The data set just exists in perpetuity. And also, now that you've trained these models on that data set, now you can get the same information much, much cheaper, or as a magnitude more quickly. So there's there's a lot of messiness there. But to directly answer your question, it's all just quantum chemistry. The one, I guess you asked about format or sort of structure. The one thing that is really annoying, and that there's been like one paper or a couple of papers that try to circumvent this, but it's currently a big problem, is there's not one sort of universally applicable quantum chemical method. There's different what are called levels of theory, but to train one of these models, you typically need consistent levels of theory across your entire data set. So we'd love to be able to combine all these different data sets that different people have made and train one model with all of them together. As I said, there's been a little bit of work in that direction, but right now you basically have to start from scratch to make a big data set to train one of these big models. Yep.
We have time for one more question. Actually, I might have one. On your last slide, you mentioned sort of like a juxtaposition between general purpose usage for foundation models and sort of domain-specific applications, and trying to find what's essential versus what's not essential.
Yeah.
Right? So I guess in the context of, for example, finding alternatives within domain, do you have any insights there in terms of how maybe logistically or in a process-oriented way you might find an alternative way to sort of avoid the harmful uses of foundation models?
Yeah. So in terms of laboratory automation, I think there are alternatives that exist now for most use cases. For sort of well-defined problems, you can use just like Bayesian optimization and sort of get as good results or maybe even a little bit better as like an LLM that's trying to optimize some process. It's possible that the LLM is truly the best thing for like open-ended exploration. That's very much yet to be seen, because like all of the papers that I'm aware of that have used LLMs for this purpose have studied like very widely studied systems where there's a lot of text probably in these models training set on, for instance, how to do okay, this is not going to mean anything for most science, but a Suzuki coupling reaction. It's like one of the most widely studied reactions in organic chemistry. Models can do that really well. Can it really do exploratory reactions well? That's sort of yet to be seen. But sort of piggybacking on a previous speaker's point, something else that I think is very obvious, but I think fewer and fewer people want to go in this route because everyone wants to chase the hot topic and no one wants to do hard work, is we don't, like, a lot of what people are using these foundation models for, we had other models for. So for instance, people are using LLMs for classification and property prediction tasks in chemistry. That is attractive if you don't have a lot of data, but there's sort of a cost benefit. It might actually be more efficient for you to just generate a little bit more data, go in the lab for a couple days or a couple weeks or whatever it takes, and then build a bespoke model. Depending on how often you're going to be using this model and sort of how hard the problem is, like that might just be a better solution in a lot of cases. But it does seem that the foundation models help a lot when you are data starved. So if it's something that's really difficult to measure or really difficult to calculate, that might still be the sort of a necessary use case right now.
Perhaps a principled way of distilling the model for the particular application.
Yeah. I mean, that's I'm not aware of anyone who's sort of worked on distillation. People have tried to do bespoke LLMs for science or like fine-tuned for science, but I'm not aware of a lot of work on distillation, and that's definitely a promising direction as well. Yeah.
Excellent. Well, let's thank the speaker again.
Yeah, come on up. I'm just